There is a particular kind of silence that hits you when you stand under a truly dark sky, far from any city, far from any light source, and you tilt your head back and let your eyes adjust. At first, there were just a handful of stars, then more still, until the sky doesn't look like a sky at all, but like a fabric that has been punctured 10,000 times by something impossibly bright on the other side. And if you stand there long enough, if you're patient, you'll start to notice a faint wash of light cutting diagonally across the darkness. That's the Milky Way. That's home. But here's the thing that tends to get lost in the everyday noise of being alive. What you're seeing when you look at that faint smear of light is not the edge of the universe. It's not even the edge of our galaxy. It's just the densest part of our own neighborhood. The galactic disk is seen from inside it, compressed by distance into something that looks like a pale river across the night. The actual universe, the full scale of what's out there, is something that no human brain has ever truly processed. Not really. We work with the numbers, we write them down, we do the math, but understanding it in the way you understand the size of your own kitchen, that's simply not available to us. And somehow, that makes it even more fascinating. Today, we're going on a journey. Not a short one. We are going to start inside the Milky Way, trace our way through its structure, its spiral arms, its glowing core, the monstrous black hole sitting at its center. And then we are going to leave. We're going to break free from our galaxy's gravitational hold and travel outward into the local group, then farther still into superclusters of galaxies that span hundreds of millions of light years, and then beyond even that, to the very edge of what we can observe and what might lie past it. And the real reason to take this journey isn't just to be impressed by large numbers, though those will certainly be coming your way. The real reason is this: the further we zoom out, the stranger and more interesting the universe becomes. At small scales, you have stars and planets, things that behave more or less the way you expect matter to behave. But as you zoom out, you start running into structures that challenge the most fundamental assumptions of modern cosmology. Walls of galaxies stretching 10 billion light-years. A mysterious gravitational force called the Great Attractor pulling hundreds of thousands of galaxies toward a single point. An invisible scaffolding of dark matter that no instrument has ever directly detected. And beyond the reach of every telescope ever built, a universe that may be infinite, may be one of countless others, or may be running on physical laws that would be completely unrecognizable to anyone alive today. This is the story of a cosmos that is far larger, far older, far stranger, and far more beautiful than anything our ancient ancestors could have imagined when they first looked up and began asking questions. And really, we haven't stopped asking since. Before we begin, a quick note on scale. When we talk about distances in space, the numbers involved are so enormous that ordinary units stop working. A kilometer is useful for measuring the distance between cities. An astronomical unit, the distance from the Earth to the Sun, about 150 million kilometers, is useful for measuring distances within our solar system. But the moment we step outside the solar system, even astronomical units become inadequate. So we switch to light years. A light year is the distance light travels in a single year, roughly 9.46 trillion kilometers. That's not a year of time, it's a unit of distance. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That means the light you see from Proxima Centauri left that star 4.24 years before it hit your eye. You're not seeing it as it is, you're seeing it as it was. And that's just the nearest star. By the time we get to the far reaches of the observable universe, we'll be looking at light that left its source nearly 13.8 billion years ago. In a very real sense, when we look deep into space, we are looking back in time. Every telescope is also a time machine. And what we see when we look backward through those billions of years is nothing short of extraordinary. There is also something worth acknowledging about the tools we use to make this journey. Everything described in this video was discovered not through direct experience, not through sending a human being there, but through the careful, painstaking analysis of light. Light collected by telescopes that cost decades of effort and billions of dollars to build. Light that has traveled for millions, hundreds of millions, even billions of years before landing on a detector the size of a dinner plate. The universe is so large that direct exploration of even a tiny fraction of it is beyond anything remotely foreseeable for our civilization. But light is the universe's own signal, constantly being broadcast from every star, every gas cloud, every accretion disk, every galaxy. All we need to do is learn to read it, and over the past few centuries, we have gotten remarkably good at reading it. Spectroscopy lets us decode the chemical composition of stars hundreds of light years away. Radio waves penetrate the dust clouds that block visible light, letting us map the structure of the galactic plane. Gravitational wave detectors allow us to hear the collisions of black holes a billion light years away, a form of cosmic eavesdropping on events that happened when the universe was less than half its current age. X-ray telescopes reveal the superheated gas of galaxy clusters and the energetic environments around neutron stars. Infrared observatories pierce through stellar nurseries that are opaque at visible wavelengths, showing us the earlier stages of planetary formation. Every wavelength of electromagnetic radiation tells a different part of the story. Every new type of detector opens a new window. And right now, in the 2020s, we are arguably living through one of the greatest golden ages of astronomical discovery in history. The James Webb Space Telescope, launched in December 2021, is peering deeper into the universe than anything before it, capturing galaxies that formed within a few 100 million years of the Big Bang and revealing their structure in stunning detail. The Event Horizon Telescope has given us our first direct images of supermassive black holes. The GEAR spacecraft is mapping the positions and motions of more than 1 billion stars within the Milky Way with a precision that was unimaginable a generation ago. And on the horizon, the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, next-generation radio arrays, and space-based gravitational wave detectors that will expand our view still further. We are, in a very real sense, at the beginning of understanding the universe. The biggest discoveries are still ahead of us, and this journey, outward from our galaxy into the cosmic web, to the edge of the observable universe and beyond, is a preview of everything that's left to find. Take a breath. Get comfortable. We're going a long way from home, and we might as well enjoy the ride. The Milky Way up, Plustin. Osef Cosmic Home. If you could somehow teleport yourself out of the Milky Way and look at it from a distance of, say, 100,000 light-years, what would you see? You'd see a barred spiral galaxy, a flattened, rotating disk of stars, gas and dust, with 2 major spiral arms and 2 minor ones curling outward from a central bar structure. At the heart of the disk, you'd see a bright, slightly boxy bulge, where stars are densely packed and ancient. Surrounding the entire disk, you'd see a spherical halo, fainter, thicker, made up of older stars clustered into globular groups. And surrounding all of that, invisible but inferred from its gravitational effects, an enormous cloud of dark matter stretching for perhaps 2 million light-years in every direction. This is the Milky Way. Our home. Our entire civilization's home. Every person who ever lived, every city ever built, every war ever fought, every painting ever made, all of it has taken place on one small rocky planet orbiting one ordinary star inside this one galaxy. And the Milky Way itself, for all its grandeur, is just one of a couple of trillion galaxies in the observable universe. The numbers that describe our galaxy are almost offensive in their size. Across its main disk, the Milky Way measures approximately 100,000 light-years from one side to the other. Though more recent research using near-infrared surveys, including work published in Nature Astronomy in 2024, suggests the structure is more complex than a simple disk with a clean edge. Scientists at Yunnan University, analyzing data from the Apogee Infrared Stellar Survey, found that the galaxy's brightness profile doesn't follow the single exponential decline that was long assumed. The outer disk, beyond about 78,000 light-years from the center, appears to flatten out in a way that suggests we may have been underestimating the galaxy's true size. In terms of half-light radius, the number that describes where half the galaxy's light is concentrated, the Milky Way appears to be meaningfully larger than the canonical single-disk model suggested. What does that disk actually contain? Conservative estimates put the number of stars in the Milky Way at around 200 to 400 billion. More recent estimates edge that number higher. In addition to those hundreds of billions of stars, the galaxy contains somewhere in the neighborhood of 25 to 100 billion brown dwarfs. Objects too small and dim to sustain hydrogen fusion, basically failed stars that glow faintly on residual heat, and orbiting many of those stars are planets, potentially over 1 trillion of them. The sheer combinatorial scale of possibilities embedded in those numbers is difficult to process. If even a tiny fraction of those planets orbit in their star's habitable zone and have conditions suitable for liquid water, the statistical argument for life existing elsewhere in the Milky Way alone becomes rather compelling. The Milky Way is a barred spiral galaxy, meaning that at its center there is an elongated bar of densely packed stars from which the spiral arms branch outward. The central bar stretches for roughly 27,000 light-years and sits roughly perpendicular to our line of sight when we look toward the galactic center. Two major spiral arms extend from the ends of this bar, the Scutum Centaurus arm and the Perseus arm. Two additional arms, the Sagittarius arm and the Norma arm, are considered secondary structures. Our own solar system sits in a smaller partial arm called the Orion arm, or the Orion spur, a bridge connecting the Sagittarius arm to the Perseus arm. We sit about 26,000 to 27,000 light-years from the galactic center. Roughly halfway out, not at the edge, not at the center, just occupying a fairly unremarkable spot in a fairly unremarkable spot in a fairly unremarkable suburb of our galaxy. What makes the spiral arms special is not that they are permanent structures. They aren't. Spiral arms are more like waves moving through the disk, density waves that cause gas and dust to compress as they pass through and trigger bursts of star formation. As a result, the spiral arms are lit up by young, hot, massive stars that blaze brilliantly for a few million years before dying in spectacular supernova explosions. Between the arms, the stellar population is older, quieter, and less spectacular. The galactic disk is thin in cosmic terms. The main disk, the thin disk that contains most of the galaxy's actively star-forming regions, is somewhere between 1,000 and 1,300 light-years thick. There is also a thicker, older disk surrounding it, about 3,000 to 6,000 light-years thick but far more diffuse, populated by older, slower-moving stars that carry the memory of the galaxy's ancient history. Observations and simulations suggest that between 11 and 8 billion years ago, the Milky Way consumed another galaxy entirely, a collision that has been dubbed Gaia Enceladus, and it was this ancient merger that seeded much of our thick disk and set off one of the great epochs of starbirth in our galaxy's long history. The entire disk rotates. Our solar system moves around the galactic center at roughly 220 kilometers per second, completing one full orbit of the galaxy approximately every 225 to 250 million years. That unit of time, the galactic year or cosmic year, puts a new frame on Earth's history. The dinosaurs went extinct less than 1 galactic year ago. The oldest rocks on Earth are only about 19 galactic years old. The universe itself is only about 60 galactic years old, and at the center of all this rotation, at the very heart of the galaxy, sits something that would stop you cold if you could somehow see it directly. Something that the laws of physics as we understand them barely allow for. A black hole of incomprehensible mass. And in May of 2022, for the first time in human history, we actually photographed it. Sagittariusa, and the Hawk of the galaxy. The center of the Milky Way is not a place you'd want to be. It is a seething, turbulent, extraordinarily violent region of space. A place where the density of stars is so high that the night sky, if you were standing on a planet anywhere near the core, would never truly be dark. Stars would crowd the sky in every direction, separated by distances so small in galactic terms that their combined light would keep even the darkest night permanently bright. Radiation pours through the region in enormous quantities. X-rays, gamma rays, ultraviolet light generated by the deaths of massive stars, by stellar winds slamming together, by the gravitational fireworks surrounding the most extreme object in our entire galaxy. That object is Sagittarius A, pronounced Sagittarius A star, and it is the supermassive black hole at the center of the Milky Way. For decades, astronomers knew it was there. They could see its presence by watching the motion of stars orbiting something invisible and incredibly massive at the galactic center. Stars screaming through space at thousands of kilometers per second, whipping around an object they never directly touched, tracing tight, elliptical orbits around a point of no return. The Nobel Prize in Physics for 2020 was awarded in part to Reinhard Genzel and Andrea Ghez, who spent years carefully tracking those stellar orbits independently, until both arrived at the same unavoidable conclusion. At the center of the Milky Way sits a supermassive black hole with a mass of approximately 4 million times that of the Sun. 4 million solar masses, contained in a region roughly 3 times smaller than Mercury's orbit around the Sun. A boundary, the event horizon, where the escape velocity exceeds the speed of light, beyond which nothing, not matter, not light, not any form of information can escape. Not because something pushes you back, but because space itself, curved to an extreme by the mass concentration, curves in such a way that all paths lead inward. There is no outward. Once you cross that line, the future only points in one direction. The stars that Genzel and Ghez spent years tracking belong to what astronomers call the S-star cluster, a remarkable group of young, hot, massive stars orbiting Sagittarius A, at distances of only a few light weeks to a few light years. These are not old stars from the early galaxy. They are young stars forming within the last few million years. Young, and their presence near the black hole raises a profound puzzle. How did they get there? Forming a star requires the collapse of a cold, dense gas cloud, and in the powerful tidal gravitational field of a supermassive black hole, those gas clouds would be ripped apart before they could collapse. Yet here these young stars are, orbiting only light weeks from the event horizon. Several explanations have been proposed. One involves the formation of massive stellar clusters outside the tidal disruption radius that then migrated inward through dynamical friction. Another involves the in situ formation of stars within the disk of gas that forms around the black hole during active accretion periods. Neither explanation is entirely satisfying. The S-stars remain one of the mysteries of the galactic center, a reminder that extreme environments produce physics we don't fully understand. On May 12, 2022, the Event Horizon Telescope Collaboration, a global network of 8 radio observatories spread across multiple continents, functioning together as a single virtual telescope the size of the Earth itself, released the first image of Sagittarius A. It appeared as a glowing, slightly uneven ring of orange-gold light surrounding a dark central shadow. That ring is not the event horizon itself, which remains invisible by definition. It's the light of superheated gas and plasma swirling at extraordinary speeds just outside the event horizon, bent and brightened by the black hole's enormous gravitational field. The shadow at the center is the projection of the event horizon against this glowing backdrop. The image was an engineering and scientific achievement that would have seemed impossible just a generation ago. The Event Horizon Telescope does not function like a conventional optical telescope. It uses a technique called very long baseline interferometry, which synchronizes radio observatories spread across the entire planet using atomic clocks, combining their data so precisely that the result is equivalent to having a single dish the diameter of Earth. Even with that Earth-sized instrument, imaging Sagittarius A was extraordinarily challenging. The black hole is 27,000 light-years away, and its apparent size in the sky is comparable to seeing a donut on the surface of the Moon from Earth. To make it harder still, Sagittarius A is a restless subject, unlike the supermassive black hole in the galaxy M87, which was imaged in 2019 and has a mass of 6.5 billion solar masses. Sagittarius A accretes material erratically and varies noticeably over periods of hours. The accretion disk flickered and shifted during the weeks of observations in April 2017, requiring astronomers to essentially take a time average of many snapshots to produce the final image. That image confirmed what general relativity predicted: the black hole shadow, the size of the ring of light, the overall geometry, all of it consistent with the mathematics of curved spacetime that Einstein wrote down more than a century ago. The region immediately surrounding Sagittarius A is densely populated. More than 6,000 stars have been identified within 3 light-years of the black hole, an extraordinary density. Among them are stars racing through their orbits at significant fractions of the speed of light. One star designated S62 passes within 17.8 astronomical units of the event horizon at its closest approach, moving at about 6.7% of the speed of light. At those velocities, the effects of general relativity are not negligible. The axis of the star's orbit shifts measurably with every pass, a phenomenon called orbital precession caused by the warping of spacetime itself. About 200 light-years from Sagittarius A, astronomers suspect the presence of a second, intermediate mass black hole, one that would bridge the gap between stellar mass black holes, which form from dying individual stars and top out at a few hundred solar masses, and supermassive ones like Sagittarius A. This hypothetical object would have a mass somewhere around 100,000 solar masses. If confirmed, it would represent one of the rarest categories of black hole, and its presence near the galactic center would have significant implications for how we understand the formation of supermassive black holes in general. Farther out from the center, between about 100 and 200 light-years, sits the central molecular zone, a vast complex of cold, dense gas with a total mass exceeding 60 million times that of the Sun. Within this region are some of the most active star-forming environments in the galaxy, nurseries where molecular clouds collapse under their own gravity and new stars ignite for the first time. Spectral analysis of this region has revealed the presence of carbon monoxide, methyl alcohol, hydrocyanic acid, and dozens of other molecules, demonstrating that the chemistry of even this extreme environment is rich and complex. The galactic center is violent, brilliant, and alien. It is also, in a very real sense, the heartbeat of everything that surrounds us. The stars that formed in the central regions of the galaxy billions of years ago seeded the disk with heavy elements: carbon, oxygen, iron, gold, elements forged in stellar cores and scattered in supernova explosions that enriched the interstellar medium from which our own sun and solar system eventually formed. We carry the legacy of the galactic center in our own chemistry. It is not a distant and irrelevant place. It is the origin of a great deal of what makes us physically possible. The galactic halo, where history is preserved in starlight. Pull back from the disk. Pull back from the bar and the spiral arms and the glowing core. Move outward in every direction, past the last lit regions of the galactic disk, and you find yourself in the Milky Way's halo. And in the halo, something remarkable happens. The noise quiets. The young, hot, short-lived stars of the disk are left behind. What remains are the oldest objects in the galaxy. Structures that formed billions of years before our sun was even a suggestion in a collapsing gas cloud. The galactic halo of the Milky Way is a roughly spherical region extending outward from the disk for somewhere between 100,000 and 300,000 light-years in all directions, though its full extent, particularly when you include the dark matter halo that envelops it all, may reach as far as 2 million light-years. Within the visible halo, spread sparsely but majestically through the darkness, are globular clusters. These are among the most beautiful and scientifically important objects in the known universe. A globular cluster is a dense, gravitationally bound sphere of stars. sometimes tens of thousands of them, sometimes hundreds of thousands, packed into a region that might only be 100 light-years across. Inside a globular cluster, the density of stars is so high that close stellar encounters are frequent, and the probability of stellar collisions over billions of years is non-negligible. The Milky Way harbors approximately 150 to 200 known globular clusters. The oldest of them are extraordinary. Some contain stars that are upward of 12 to 13 billion years old, meaning they formed when the universe itself was barely a few 100 million years old. They are relics, time capsules from the very earliest period of cosmic history. Studying the globular clusters in the Milky Way's halo tells us a tremendous amount about how the galaxy formed. Not all of them are native. A significant number were captured from dwarf galaxies that the Milky Way consumed over billions of years of galactic growth. This process of cannibalization, larger galaxies eating smaller ones, is not rare or violent in the way a predator eating prey is violent. It's slow. It unfolds over hundreds of millions of years. The gravitational field of a large galaxy like the Milky Way gradually stretches and distorts a smaller companion, pulling its stars away in long tidal streams until what was once a distinct galaxy has been dissolved into the larger one, and its members have joined the general stellar population. The Sagittarius dwarf spheroidal galaxy, a small companion galaxy currently being disrupted by the Milky Way's tidal forces, is one of the most vivid examples of this process. The Sagittarius stream, a long looping arc of stars torn from this dwarf galaxy, has been traced wrapping almost entirely around the Milky Way, tilted steeply out of the main plane of the disk. Some estimates suggest this structure could contain several 100 million stars, all of them originally belonging to a separate galaxy that has now been almost entirely consumed. In a few billion more years, the Sagittarius dwarf spheroidal will likely cease to exist as a distinct structure at all. There is also a broader stellar stream called the Canis Major overdensity, discovered in the early 2000s and debated since, which may represent the remnants of another dwarf galaxy that orbited so closely to the Milky Way that it was essentially torn apart. This stream, if it is indeed the debris of a swallowed galaxy and not a feature of the disk itself, has already wrapped around our galaxy multiple times, a filament of roughly 100 million solar masses of stellar material, mixed into the outskirts of the galactic disk. Globular clusters themselves deserve more than a passing mention, because despite being old, some of the oldest coherent objects in the universe, they are not static or dead. They are active systems undergoing their own internal dynamics. And some of those dynamics are extraordinary. Blue straggler stars, for instance, are stars found in globular clusters that appear younger and more massive than they should be given the age of the cluster. The current thinking is that they formed through stellar mergers or mass transfer, one star stealing material from a companion, or two stars colliding directly, creating a new star that appears younger than its surroundings. In the dense cores of globular clusters, where stars are packed closely enough that close encounters are common, these collisions are not vanishingly rare events. Over billions of years, a globular cluster becomes a laboratory for stellar interactions that almost never occur in the more diffuse regions of the galactic disk. Some globular clusters also host unusual objects at their centers. There is growing evidence, still not definitive in all cases, that some globular clusters contain intermediate mass black holes at their centers, analogous to the supermassive black holes at the centers of galaxies, but much smaller, perhaps in the range of hundreds to tens of thousands of solar masses. If confirmed through future observations and gravitational wave detections, these intermediate mass black holes would represent a critical missing link in our understanding of how black holes grow across cosmic time. The Milky Way satellite galaxy system has been continuously expanding as more sensitive surveys come online. As recently as the early 2000s, the number of confirmed dwarf galaxy satellites was only a handful. Today, with the benefit of deep sky surveys, that number has grown to more than 50 confirmed satellites and candidates, with potentially many more remaining undetected in the southern sky or hiding behind the dense stellar background of the galactic disk. Each new discovery adds a data point to one of the most important debates in modern astrophysics: whether the distribution of these dwarfs around the Milky Way matches the distribution predicted by cold dark matter models of structure formation, or whether the observed distribution requires modifications to our understanding of dark matter or gravity itself. But the most significant neighbors in the immediate halo environment are the Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere with the naked eye, appearing as detached fragments of the Milky Way glowing softly against the black sky. The Large Magellanic Cloud sits about 160,000 light-years away and contains around 20 to 30 billion stars. The Small Magellanic Cloud is about 200,000 light-years away. Both are gravitationally connected to each other by a bridge of neutral hydrogen gas, and both are gravitationally connected to the Milky Way in ways that astronomers are still working to fully understand. The Large Magellanic Cloud is a feast for astronomers. It housed the Tarantula Nebula, known formally as 30 Doradus, a star-forming region so extraordinarily active that it is the most productive stellar nursery in the entire local group of galaxies. If the Tarantula Nebula were placed at the same distance from Earth as the Orion Nebula, itself considered impressively large and close, it would be bright enough to cast shadows. It spans roughly 550 light-years and contains some of the most massive and luminous stars known. In 2025, astronomers at the Center for Astrophysics announced strong evidence for a supermassive black hole inside the Large Magellanic Cloud, with an estimated mass of around 600,000 times that of the Sun, the second closest supermassive black hole to us after Sagittarius A. The Large Magellanic Cloud is also predicted to collide with the Milky Way. Not with Andromeda, not with some distant galaxy. With us. Models suggest this merger will begin in roughly 2.4 billion years. It's likely to trigger an enormous burst of star formation, possibly even destabilize Sagittarius A enough to temporarily reactivate it as a quasar, flooding our galaxy with radiation. Compared to the Andromeda scenario we'll get to shortly, this is the more certain and more immediate galactic event on our future calendar. And surrounding all of this, the disk, the halo, the satellite galaxies, the captured globular clusters and stellar streams, is the dark matter halo. Invisible to every detector yet built, detectable only through its gravitational influence. An enormous sphere of mysterious substance that contributes the overwhelming majority of the Milky Way's total mass and that reaches out into space far beyond anything you could photograph, even in principle. This dark halo is the scaffolding that holds everything together, and understanding it is one of the defining scientific challenges of our century. The local group, OS Sectic Nateward, far enough that the Milky Way shrinks from a vast structure spanning 100,000 light-years into something that looks, at this distance, like a tightly wound pinwheel sitting in the darkness. At this scale, you can start to see the company we keep, our nearest galactic neighbors, the other members of what astronomers call the local group. The local group is a collection of more than 50 galaxies spread across an area of space roughly 10 million light-years in diameter. It is gravitationally bound, meaning that all the galaxies within it are locked into a common fate, their individual motions ultimately controlled by the combined gravitational field of the whole structure. Some of those galaxies are tiny dwarfs, irregular collections of a few million stars that orbit the larger members like moons orbit planets. Others are more substantial, and 3 of them dominate the group entirely: the Milky Way, the Triangulum Galaxy, and the Andromeda Galaxy. The Triangulum Galaxy, also known as Messier 33, sits about 2.73 million light-years from us. It is a spiral galaxy, a genuine full-scale spiral, but considerably smaller than either the Milky Way or Andromeda. Its stellar population is estimated at somewhere between 40 billion and 60 billion stars, making it perhaps a quarter the size of the Milky Way in terms of stellar content. What makes Triangulum particularly interesting to astronomers is that it appears to be in a complex gravitational relationship with Andromeda, possibly on an orbit that has brought the two galaxies close together before. The bridge of gas connecting Triangulum to Andromeda hints at past tidal interactions between them. Scattered throughout the local group, alongside these three main galaxies, are the dwarf members: the Leo I dwarf, the Leo II dwarf, the Sculptor dwarf, the Sculptor dwarf, the Fornax dwarf, the Carina dwarf, and many others, some containing only a few 100 million stars, some smaller still. These dwarf galaxies are scientifically important in a subtle but powerful way. They are the most dark matter-dominated objects known. In the smallest of them, dark matter outweighs visible stellar matter by factors of hundreds to one. They are, in a very literal sense, mostly darkness held together by the faintest gravitational thread, decorated with a scattering of stars that serve as traces of the underlying invisible mass. The distribution of dwarf galaxies in the local group has actually been a source of some friction between observation and theory. Standard models of structure formation in the universe, models based on cold dark matter particles, predict that a galaxy the size of the Milky Way should be accompanied by thousands of smaller satellite galaxies. What we observe instead are a few dozen. This gap between prediction and observation is known as the missing satellites problem. And while some of the discrepancy can be explained by the fact that very small and faint dwarf galaxies are simply hard to detect, the full explanation remains an area of active research. In recent years, surveys using sensitive telescopes, including the Dark Energy Survey and precursors to the Legacy Survey of Space and Time that will eventually be conducted at the Vera Rubin Observatory, have turned up dozens of ultra-faint dwarf galaxies, slowly filling in the census of our neighborhood. But the puzzle is not entirely resolved. There is also a related problem called the too big to fail problem, which concerns the internal properties of the largest dwarf satellite galaxies. Simulations predict that the densest, most massive dark matter substructures around a galaxy like the Milky Way should have formed the largest satellite galaxies. But the observed large dwarf galaxies appear to have lower central densities than those simulations predict. Either the simulations are missing some physics, perhaps the feedback from stellar explosions and radiation that can heat and redistribute dark matter in the central regions of small galaxies. Or dark matter is not quite the cold, collisionless substance the standard model assumes. These are not obscure corner cases. They are active, lively debates at the front lines of cosmology, and they reveal that even our well-established picture of structure formation at the scale of galaxies and below has room for significant revision. This is not a weakness of the science. It's how science works. The more precisely we measure, the more clearly we can see where the models need refinement. The total mass of the local group, when you account for all the dark matter in the dark halos of its member galaxies, is estimated at somewhere between 2 and 3 trillion solar masses. For context, if you compress the entire mass of the Sun, itself 333,000 times the mass of Earth, into a single object, and then did that 2 trillion times, you would be approaching the mass of our cosmic neighborhood. It is a staggering concentration of material assembled over billions of years through gravitational attraction, galaxy mergers, and the gradual consumption of smaller structures by larger ones. And this neighborhood is not static. Every galaxy within the local group is moving, pulled by the gravity of everything around it, locked in orbits and trajectories that will play out over timescales of billions of years. The fate of these galaxies, of all of them, including our own, is decided by those trajectories. And for the Milky Way, the most consequential trajectory in the local group belongs to Andromeda. The Andromeda galaxy, Messier 31, is the largest member of the local group. It sits approximately 2.5 million light-years away, close enough that it is the most distant object routinely visible to the naked eye on a clear dark night, appearing as a faint smudge in the constellation Andromeda. It contains roughly 1 trillion stars, more than 3 times the stellar population of the Milky Way, and it has its own supermassive black hole at its center, weighing in at around 100 million solar masses, roughly 25 times the mass of Sagittarius A. It is spiral in structure, broadly similar to the Milky Way in its architecture, but larger and somewhat more quiescent in terms of active star formation. its gas supply partially depleted by past merger events. Andromeda is not a perfect, pristine spiral. Evidence suggests it has already undergone a significant merger event in its past, perhaps within the last few billion years, that disrupted its disk and produced the broad, diffuse stellar halo of stripped material that surrounds it today. Multiple shell structures in Andromeda's halo, shells being the characteristic signature of a past galactic merger, suggest that a smaller galaxy was consumed and torn apart, depositing its stars in the expanding concentric patterns that we observe. Andromeda is, like the Milky Way, not a hermit but a serial cannibal, growing through consumption. And it is moving toward us. Right now, as you read this, Andromeda and the Milky Way are closing the gap between them at approximately 110 kilometers per second. The light carrying information about Andromeda's current position won't reach us for 2.5 million years. What we see in the sky tonight is not where Andromeda is. It's where Andromeda was when humans were not yet humans. What is happening there right now, we simply cannot know. The Andromeda question, a future Gwytton in gravitational pull. For most of the past decade, the consensus in astronomy was that the collision between the Milky Way and Andromeda was essentially inevitable and essentially scheduled, a head-on galactic smash-up predicted to begin in about 4 to 5 billion years, with the two galaxies eventually merging completely into a single elliptical galaxy over the following 2 to 3 billion years. Astrophysicists even gave the merger product a name, Milkomeda, or sometimes Milkdromeda. Simulations run with the older data painted a vivid picture, two spirals closing in, passing through each other, stars flung in long tidal arcs, a burst of star formation ignited by the compression of gas clouds, the supermassive black holes of each galaxy slowly spiraling toward each other over millions of years until they, too, merged in a final cataclysm of gravitational wave emission. But in 2025, a study published in Nature Astronomy forced astronomers to revise that picture substantially. Researchers at the University of Helsinki, led by Till Sawala, combined the most precise measurements available from the Hubble Space Telescope and the European Space Agency's Gaia spacecraft, which has been measuring the positions and motions of more than 1 billion stars across the sky with extraordinary precision, with updated mass estimates for the local group, and ran 100,000 Monte Carlo simulations covering 10 billion years of future time. What they found changed the narrative. When the influence of Andromeda's large satellite galaxy, the Triangulum Galaxy, and the Milky Way's own satellite, the Large Magellanic Cloud, are factored in, the dynamics become considerably more complex. The Large Magellanic Cloud, in particular, orbits on a plane that runs roughly perpendicular to the Milky Way Andromeda approach trajectory, and its gravitational influence tends to pull the Milky Way slightly off course, reducing the probability of a direct collision. Across all 100,000 simulated futures, the chance of a head-on collision within the next 10 billion years was found to be only about 50%. In many scenarios, the two galaxies fly past each other, separated by up to 500,000 light-years, then gradually fall back together over a much longer timescale driven by dynamical friction between their vast dark matter halos. In other scenarios, they don't even come close enough for that process to work effectively and continue orbiting each other indefinitely. There remains a roughly 2% probability of a direct collision in just 4 to 5 billion years, close to the old NASA prediction. But the story is now unmistakably one of deep uncertainty rather than cosmological inevitability. What would the collision actually feel like if you were somehow observing it from inside the Milky Way? The first thing to understand, the thing that surprises almost everyone, is that in a collision between two galaxies, individual stars almost never collide with each other. This seems counterintuitive when you imagine two galaxies slamming together, but consider the density. The average distance between stars and the Milky Way's disk is somewhere around 4 to 5 light-years. If you scaled the Sun down to the size of a ping-pong ball, the nearest star would be a pea sitting approximately 1,100 kilometers away. At that scale, the entire Milky Way galaxy would be about 30 million kilometers wide. Two ping-pong balls, billions 100 kilometers apart, embedded in a sphere 30 million kilometers across. passing through a mirror image of themselves. The probability of any two ping-pong balls hitting each other is essentially zero. What would change dramatically is the sky. Over the tens of millions of years of the initial close approach, Andromeda would grow larger and larger in the night sky, eventually spanning the horizon like a vast, glowing cloud of stars. The distribution of stars around us would shift as tidal forces reshuffled our galactic neighborhood. New stars would ignite in enormous numbers as gas clouds were compressed. The background of the sky would become brighter, not darker. Whether or not a merger eventually happens, the collision event, or close flyby, would reshape the galaxy in ways that would persist for billions of years. Our solar system might be flung to an entirely different region of the merged galaxy. Models suggest a roughly 50% chance that the Sun ends up 3 times farther from the new galactic center than it is today, and approximately a 12% chance of being ejected from the merged system entirely, cast out into intergalactic space to drift alone, planetless or with planets through the void. None of this, it bears pointing out, would be catastrophic for any life on Earth. Or rather, it wouldn't be the collision's fault. Long before Andromeda threatens anything, the Sun itself will have expanded into a red giant, making Earth's surface uninhabitable approximately 1 billion years from now, and swallowing the inner planets entirely around 5 to 7 billion years from now. The galactic merger, if it happens on the shorter end of projections, will overlap with the late stages of the Sun's life. Earth will be gone. What happens to the Milky Way after that will happen without us. But even without us, the story continues. And it continues at scale so large that the local group itself is just a footnote. Lanika. The Supple cluster we call home. Zoom out further. Far enough that the local group, all 50-plus galaxies of it, spanning 10 million light-years, fits comfortably in the frame. At this scale, you can see that the local group is not isolated. It's part of something larger, the Virgo supercluster, a concentration of galaxy groups and clusters spread across an area roughly 110 million light-years across, containing somewhere between 100 and 2,000 galaxies, depending on how you define the boundaries. The Milky Way's local group sits in the outer fringes of the Virgo supercluster, near its periphery, not at its center. But in 2014, astronomers made a discovery that reframed the Virgo supercluster entirely. A team led by R. Brent Tully at the University of Hawaii, using a new catalog of galaxy distances and velocities called Cosmic Flowers 2, developed a novel way of thinking about cosmic structure. Rather than defining superclusters by density, by looking for regions where galaxies pile up, they defined them by motion. Specifically, they looked at which galaxies were flowing toward a common gravitational center. A supercluster, in this framework, is a gravitational watershed, a region where all local motions of galaxies ultimately trend inward toward a shared attractor. When they applied this framework to our cosmic neighborhood, the result was startling. The Virgo supercluster, rather than being a structure in its own right, turned out to be just a single tributary flowing into something far more enormous. They called it Laniakea, a name drawn from Hawaiian meaning immeasurable heaven. Laniakea spans approximately 500 million light-years across. It contains something on the order of 100,000 large galaxies, with a total mass of roughly 100 quadrillion solar masses, a 1 followed by 17 zeros. Our entire galaxy, with its hundreds of billions of stars, its trillion planets, its supermassive black hole, its vast dark matter halo, is an almost infinitesimally small component of Laniakea, the gravitational center of Laniakea. The point toward which all those 100,000 galaxies are slowly flowing is a region called the Great Attractor. It sits about 250 million light-years away from us, in the direction of the constellations Centaurus and Norma. And for a long time it was one of the most frustrating mysteries in observational astronomy because it lies almost directly behind the plane of the Milky Way as seen from Earth. The dense band of dust and stars along the galactic equator blocks our view in optical wavelengths, placing the Great Attractor squarely in what astronomers call the zone of avoidance. The Milky Way is hurtling toward the Great Attractor at approximately 600 to 1,000 kilometers per second. Not just the Milky Way, the entire local group, the entire Virgo supercluster, all of it drifting, on timescales of billions of years, toward this gravitational focal point. The Great Attractor itself appears to be associated with the Norma cluster, a rich concentration of hundreds of galaxies embedded in a dense wall of matter called the Norma wall. Radio and X-ray observations, which penetrate the dust clouds that block visible light, have revealed partial glimpses of what lies behind the zone of avoidance. But the full picture remains incomplete. What does appear clear is that the Great Attractor is itself flowing towards something even larger. The Shapley supercluster, one of the largest concentrations of mass in the nearby universe, sitting roughly 650 million light-years away. Some recent research from Tully's group at the University of Hawaii, published in 2024, even suggests that Laniakea itself may be a sub-basin within a still larger gravitational structure centered on the Shapley concentration, a possible superstructure roughly 10 times the volume of Laniakea. If confirmed, our cosmic address would need another line. There is something philosophically striking about this. The history of astronomy is a history of finding out that we are not at the center of anything. The Earth is not at the center of the solar system. The Sun is not at the center of the Milky Way. The Milky Way is not at the center of the local group. The local group is not at the center of the Virgo supercluster. The Virgo supercluster is not at the center of Laniakea. And Laniakea itself may be drifting toward a larger structure centered elsewhere. We exist at the periphery of peripheries, nested within cosmic structures that diminish in significance with every layer you add. And yet, simultaneously, every one of those structures is made of the same atoms, the same protons, the same electrons, the same forces, the same fundamental physics that governs the behavior of every particle in your body also governs the motion of every galaxy in Laniakea. The universe is one continuous thing, operating on one set of rules, and we are a part of it. The cosmic W ends as Tarkish on the grandest scale. Zoom out more, way more. Step back until Laniakea, that colossal structure spanning 500 million light-years and containing 100,000 galaxies, shrinks to a modest knot in a much larger pattern. At this distance, you're not looking at individual galaxies anymore. You're looking at the universe's large-scale structure and what it reveals about the history and future of everything. The universe, at the largest scales, is not a uniform distribution of galaxies randomly scattered through space. It is a structure, a specific, recurring, profoundly beautiful structure that astronomers and cosmologists call the cosmic web. And once you see it, once you truly understand what you're looking at, it will change how you think about the universe forever. The cosmic web is built from three basic components: filaments, walls, and voids. Filaments are long, thread-like concentrations of matter, galaxies strung along the gravitational highways between massive clusters, connected by the dark matter scaffolding that runs through all of space. Walls are broader, flatter concentrations of galaxies, sheet-like structures where many filaments converge. Voids are the spaces between all of this. Enormous, approximately spherical regions of space where the density of matter is far below the cosmic average. In the deepest voids, barely anything exists at all. This structure is not random. It is the direct consequence of quantum fluctuations in the early universe, tiny variations in density that existed in the first fractions of a second after the Big Bang, and that inflation amplified to cosmic scales. Over billions of years, gravity has done the rest, pulling matter along those original density variations, concentrating it in filaments and nodes while draining the regions in between and enlarging the voids. The cosmic web we see today is, in a sense, a fossilized record of the conditions that existed in the universe's earliest moments. written in the distribution of galaxies across billions of light-years of space. The largest structures in the known universe sit at the intersections of this web and along its longest filaments. The Sloan Great Wall, identified in 2003 through the Sloan Digital Sky Survey, stretches for approximately 1.4 billion light-years, an almost unimaginably long chain of galaxy clusters and superclusters, discovered by mapping the three-dimensional distribution of hundreds of thousands of galaxies. Before its discovery, such a structure was thought to be at the very limit of what the universe could produce, given the amount of time that had elapsed since the Big Bang. Then came the Hercules Corona Borealis Great Wall, and it upended everything. Discovered in 2013 and named for the constellations in which it appears to be concentrated, the Hercules Corona Borealis Great Wall is the largest known structure in the observable universe. It was not found through a traditional galaxy survey, but through an analysis of the distribution of gamma-ray bursts, the most energetic explosions in the universe, produced when massive stars die or when neutron stars merge. Gamma-ray bursts are bright enough to be detected across essentially the entire observable universe, making them useful as tracers of the large-scale distribution of matter. And in one particular region of the sky, gamma-ray bursts were found to be clustering in a way that implied an overdensity of matter spanning an almost incomprehensible scale. The current best estimate of the Hercules Corona Borealis Great Wall's extent is approximately 10 billion light-years. For perspective, the observable universe is about 93 billion light-years in diameter. This structure stretches across more than 1/10 the diameter of everything we can see. A beam of light, traveling at 300,000 kilometers per second, the fastest speed physics allows, would take 10 billion years to cross it. That's nearly 3/4 of the age of the universe itself. It is worth pausing on that fact. This structure formed within a universe that has only existed for 13.8 billion years. And yet it stretches for 10 billion light-years. According to standard cosmological theory, specifically the principle of cosmic homogeneity, which holds that the universe should look the same in all directions and at all scales above a few 100 million light-years, a structure this large should not exist. The mathematical models that describe how matter clusters under gravity predict that beyond a certain scale, the universe should be smooth, featureless, statistically uniform. The Hercules Corona Borealis Great Wall violates that expectation by a factor that is difficult to explain away. There is still debate about whether it is truly a gravitationally coherent structure or simply a statistical overdensity in the gamma-ray burst distribution. The gamma-ray burst catalog that revealed it is not as densely sampled as optical galaxy surveys, and systematic biases in the data could potentially produce the appearance of a structure without one truly being there. Future surveys with more complete coverage will be essential to settle the question. But even if the Hercules Corona Borealis Great Wall turns out to be partially a statistical artifact, the very fact that it might exist, that the universe might have produced a structure that large, tells us something important. It tells us that either our understanding of the early universe and how structure forms is incomplete, or our statistical tools are not capturing all the real structure that's there, or the universe is operating in ways that the current standard model doesn't fully account for. Any one of those possibilities is scientifically exciting. The voids between these great structures are just as interesting in their own way. The largest known void is the Bootes Void, discovered in 1981, which spans approximately 330 million light-years and is conspicuously underdense. It contains only about 60 known galaxies, where the average region of that size would contain hundreds or thousands. Within the void, the expansion of the universe appears to proceed differently than in the surrounding filaments, and some researchers have suggested that voids are not just passively empty, but actively pumped, with dark energy driving the expansion of space within them faster than in denser regions. The Bootes Void is so empty relative to its surroundings that when it was first discovered, some astronomers jokingly described it as too empty, as though the universe had simply forgotten to fill it in. Voids play a surprisingly important role in cosmology beyond their novelty. Because they are the regions of lowest density in the universe, they are also the regions least affected by the gravitational pull of surrounding matter. Their expansion is driven almost entirely by dark energy, with minimal interference from gravitational attraction. This makes them excellent laboratories for studying dark energy's behavior. By carefully measuring the shapes and sizes of cosmic voids at different epochs of cosmic history, different redshifts, astronomers can trace how dark energy has affected the expansion rate of the universe over time. The Euclid mission is specifically designed to use this technique, among others. What also emerges from looking at the cosmic web in its full breadth is a recognition of cosmic time depth. The cosmic web we observe today, the distribution of filaments, walls, nodes, and voids, did not spring into existence fully formed. It has been growing and evolving since the universe was less than 1 billion years old. In the early universe, the density contrasts were tiny. The universe was nearly uniform. Over time, gravity has amplified those tiny contrasts, pulling matter into ever denser structures, draining the voids of what little material they had, and building the intricate architecture we see today. This process of gravitational collapse and structure growth has a name: cosmic structure formation, and it is governed almost entirely by dark matter. Before the universe was cool enough for atoms to form, for the first 375,000 years after the Big Bang, ordinary matter was tightly coupled to radiation, forming a hot plasma in which sound waves propagated. Dark matter, however, was unaffected by this radiation pressure and began clumping immediately. By the time atoms formed and ordinary matter was freed from the plasma, the dark matter had already created a network of gravitational potential wells, a cosmic scaffolding, and ordinary matter simply fell into those pre-existing wells. The cosmic web we observe is, in the most fundamental sense, the shadow of a dark matter web. The galaxies and filaments we can see are tracing something we cannot see at all. This is one of the more philosophically disorienting facts about modern cosmology. The visible universe, everything that produces or reflects light, is not the primary actor in its own story. It's decoration on a canvas that is mostly invisible. The cosmic web is not decorative. It is the most fundamental organizational principle of the universe at large scales, and understanding it in detail, measuring the exact distribution of filaments and voids, tracing the dark matter that underlies the visible structure, is one of the central goals of next-generation astronomical surveys. The Euclid mission, launched by the European Space Agency in 2023, is currently mapping the distribution of galaxies across a vast swath of the sky, aiming to trace the growth of structure over the last 10 billion years and precisely characterize the role of dark energy in shaping what we see. Dark matter, the invisible architecture of everything. We've mentioned dark matter several times already, because it's essentially impossible to talk about galaxies, galaxy clusters, the cosmic web, or the large-scale structure of the universe without it. But what exactly is it? And how do we know it's there if we can't see it? The story of dark matter is one of the most compelling detective stories in the history of science, and it begins not with a particle physicist in a laboratory, but with a Swiss astronomer looking at a cluster of galaxies in the 1930s. Fritz Zwicky was observing the Coma cluster, a rich collection of more than 1,000 galaxies, when he noticed something peculiar. He measured the velocities of individual galaxies within the cluster, and then calculated how much mass the cluster would need to have in order to keep those galaxies bound together gravitationally. The answer he got was wildly inconsistent with the mass he could actually observe. The visible matter in the cluster, the stars, the galaxies, the gas, was far, far less than what was needed. He called the missing component Dunkel Materie, dark matter, and for decades, nobody paid much attention to him. The decisive confirmation came in the 1970s, largely through the work of astronomer Vera Rubin and her colleagues. Rubin was studying the rotation curves of spiral galaxies, measuring how fast stars at different distances from the galactic center were orbiting. Based on simple Newtonian gravity, you'd expect stars in the outer regions of a galaxy, far from the concentration of mass at the center, to orbit more slowly, just as the outer planets of the solar system orbit the Sun more slowly than the inner ones. What Rubin found instead was that stars in the outer regions of many spiral galaxies were orbiting just as fast as stars much closer to the center. The rotation curve was flat, not declining. This could only be explained if there was additional mass, invisible mass, distributed throughout the galaxy and extending far beyond its visible edge, holding the outer stars in their orbits by sheer gravitational force. Today, the evidence for dark matter is overwhelming and comes from many independent directions. Gravitational lensing, the bending of light from background galaxies by the mass of foreground clusters, reveals mass distributions that extend far beyond the visible matter. The detailed pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, encodes information about the ratio of dark matter to ordinary matter in the early universe and is entirely consistent with dark matter making up about 27% of the universe's total mass energy content. The velocities of galaxies and clusters, the large-scale structure of the cosmic web itself, all of it points to the same conclusion. In the standard cosmological model, dark matter makes up 27% of the universe's mass energy content. Ordinary matter, atoms, protons, neutrons, everything you have ever touched or seen, makes up only about 5%. The remaining 68% is dark energy, which we'll get to in a moment. In other words, all the visible matter in the universe, every star, every planet, every galaxy, every nebula, every black hole, every human being, is less than 5% of what's out there. We are a thin veneer of familiar physics floating on top of a universe dominated by things we fundamentally do not understand. What is dark matter made of? Honestly, we don't know. It doesn't interact with light, which means it doesn't absorb it, emit it, or reflect it. It doesn't interact with the electromagnetic force at all, which is why it's invisible to every telescope ever built. It interacts with gravity, which is how we know it's there. And it appears to be cold, meaning the dark matter particles, assuming they are particles, were moving slowly relative to the speed of light in the early universe, which gives us the type of structure formation we observe. Proposed candidates include WIMPs, weakly interacting massive particles, hypothetical particles that would have the right mass and interaction properties to be produced in the early universe in the observed abundance. They've been searched for in underground detectors, where any rare interaction with ordinary matter would produce a detectable recoil. At particle accelerators, including the Large Hadron Collider at CERN, and by looking for their signatures in cosmic ray experiments. So far, despite impressive experimental sensitivity, no direct detection has been confirmed. Other candidates include axions, extremely light particles originally proposed to solve a different problem in particle physics, and primordial black holes formed in the early universe. More exotic proposals include entire sectors of dark physics, shadow forces and shadow atoms interacting only gravitationally with the world we can see. The absence of a detected dark matter particle is not evidence that dark matter doesn't exist. The evidence that it does exist is, at this point, enormous. But the absence of a detection does tell us that whatever it is substantially harder to find than the most popular theoretical models predicted. The universe, as usual, is not cooperating with our expectations. It is worth pausing to think about what we know about dark matter from structure. The cosmic web we observe, the distribution of filaments, walls, clusters, and voids across hundreds of millions of light-years, is one of the most powerful constraints on the nature of dark matter. Cold dark matter models, in which the dark matter particles were moving slowly relative to the speed of light in the early universe, produce a cosmic web that matches observations extraordinarily well at large scales. The sizes of galaxy clusters, the clustering of galaxies in surveys, the baryon acoustic oscillations, the faint imprint of sound waves from the early universe that appear as a preferred scale in the distribution of galaxies, all are consistent with cold dark matter predictions. But at small scales, below about 1,000,000 light-years, at the level of individual dwarf galaxies, the agreement between cold dark matter predictions and observation becomes messier. This is where the missing satellites problem, the too big to fail problem, and another puzzle called the Corcus problem all arise. Cold dark matter simulations predict that the density of dark matter should peak sharply toward the centers of galaxies, creating a steep cusp. Observations of dwarf galaxies often instead reveal a flat central density, a core. This discrepancy has led to proposals that dark matter may interact with itself in ways beyond simple gravity, a scenario called self-interacting dark matter, which would allow collisions between dark matter particles to redistribute material and flatten the central density profile. Other researchers have suggested that the resolution lies not with the dark matter itself, but with the ordinary matter. Supernova explosions and stellar feedback processes in small galaxies are energetic enough to drive gas out of the galaxy's center, and as the gas moves, it carries gravitational influence with it, gradually flattening the dark matter density profile through repeated cycles of gas inflow and outflow. Simulations that include detailed models of stellar feedback can reproduce the observed core-like profiles in at least some cases, potentially resolving the discrepancy without modifying the nature of dark matter at all. The debate is ongoing and unresolved. What it demonstrates is that our understanding of how dark matter and ordinary matter interact to produce the galaxies we observe, even the galaxies we can study in our own backyard, is still incomplete. The universe at small scales is telling us something we haven't fully understood yet. Every generation of larger simulations and more powerful telescopes gives us new data points to work with, and the picture continues to evolve. Dark matter does not just exist as a passive background. It was the seed of everything we see. In the early universe, dark matter began clumping along the overdense regions established by inflation. And ordinary matter fell into the gravitational potential wells that dark matter created. The first galaxies formed in the densest dark matter clumps. The filaments of the cosmic web traced the dark matter filaments. Galaxy clusters sit at the densest dark matter nodes. The architecture of the visible universe is a map drawn in ordinary matter on a canvas made of dark matter. Dark energy, the observable universa, and the cosmic horizon. We've established that 27% of the universe is dark matter. That leaves 68% unaccounted for. That 68% is dark energy. And it is, if anything, even more mysterious than dark matter. The discovery of dark energy was entirely unexpected. As recently as the 1990s, most cosmologists assumed that the expansion of the universe that had been occurring since the Big Bang was gradually slowing down. Gravity, after all, is an attractive force. All the matter in the universe, distributed across all of space, should be pulling back on the expansion, decelerating it. The question astronomers were trying to answer in the late 1990s was not whether the expansion was slowing down, but how fast it was slowing down. Two independent teams were working on this problem. Both were using tight-wire supernovae as standard candles, a technique based on the observation that these particular explosions always achieve approximately the same maximum brightness, making them useful as distance indicators. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it must be. And if you combine that distance with a measurement of how fast the object is receding from us, derived from the redshift of its light, you can trace the history of the universe's expansion. What both teams found, simultaneously and independently in 1998, was that the distant supernovae were fainter than they should be. Not brighter, fainter. Which meant they were farther away than expected. Which meant the universe was not decelerating. It was accelerating. The expansion was speeding up. This result earned the Nobel Prize in Physics for 2011. Awarded to Saul Perlmutter, Brian Schmidt, and Adam Riess. And it introduced one of the most vexing problems in all of science. What is causing the acceleration? The leading explanation involves a form of energy that is intrinsic to space itself. a constant energy density of the vacuum, often associated with Einstein's cosmological constant. As space expands, more space comes into existence. And if each new unit of space carries this intrinsic energy, then the total amount of dark energy increases as the universe grows, which drives more expansion, which creates more space, which creates more energy, in a self-reinforcing acceleration. The universe is running away from itself. This has extraordinary consequences for the long-term future. Galaxies that are currently receding from us at less than the speed of light will, over time, recede faster and faster as the expansion accelerates. Eventually, their light will no longer be able to reach us at all. The universe is developing a horizon, not a wall, not a boundary in space, but a boundary in causality. Light emitted today from objects beyond a certain distance will never reach us, and objects that are currently within our observable universe but moving away faster than light will eventually recede beyond our ability to ever communicate with them. Right now, the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46.5 billion light-years, giving a total diameter of about 93 billion light-years. The universe is 13.8 billion years old, so you might expect the observable universe to be 27.6 billion light-years in diameter. But the universe has been expanding during the time light has been traveling, which is why the figure is much larger. The light we see from the most distant objects was emitted when those objects were much closer to us. They have since moved far away. One of the most remarkable objects we can detect at the very edge of the observable universe is the cosmic microwave background radiation, the CMB. When the universe was about 375,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was filled with an opaque plasma. Photons could barely travel any distance before being scattered. When atoms formed, the universe became transparent, and the photons that had been trapped in that plasma streamed freely outward in all directions. Those photons, now stretched by the expansion of the universe to microwave wavelengths, are what we detect today as the CMB. They represent the farthest light it is physically possible to receive from the early universe. They are the universe's baby picture, a snapshot of conditions when it was less than 400,000 years old. The CMB is extraordinarily uniform. The temperature of the microwave background varies by only about 1 part in 100,000 across the sky. But those tiny variations are information-rich. They encode the distribution of matter in the early universe, the seeds of all the structure that would later form. Analyzers of CMB temperature maps by the WMAP and Planck satellites have been used to determine the age of the universe, its geometry, flat to extraordinary precision. Its composition, 5% ordinary matter, 27% dark matter, 68% dark energy, and the parameters of cosmic inflation. The CMB has been one of the most powerful scientific instruments ever pointed at the universe. Not a physical instrument, but a message from the universe's own infancy. Beyond the CMB, beyond the surface of last scattering, lies the cosmic Dark Ages, a period of several hundred million years after the CMB was released and before the first stars ignited, during which the universe was filled with neutral hydrogen and helium, dark, cold, and featureless. No starlight, no galaxy light, just hydrogen slowly collapsing under gravity into the seeds of what would become the first galaxies, the first stars, so-called population 3 stars, hypothetical massive objects formed entirely from hydrogen and helium with no heavier elements, would have lit up the universe for the first time during this period, reionizing the surrounding hydrogen and initiating the epoch of reionization. These first stars have never been directly observed, but they are one of the primary targets of JWST's deep field observations, and hints of their influence on the surrounding gas have been detected in the spectra of distant quasars. Within this 93 billion light-year sphere are an estimated 2 trillion galaxies. 2 trillion. Each contains hundreds of billions of stars, each with, statistically speaking, at least one planet per star. The observable universe contains more stars than all the grains of sand on all the beaches and deserts on Earth. A comparison that, the more you sit with it, begins to dissolve the concept of large and small entirely. But here's the thing. The observable universe is not the universe. It is, by definition, only the portion of the universe from which light has had time to reach us. Beyond our observable horizon lies more space, much more. And because the universe is likely much larger than what we can see, perhaps vastly so, that space is populated with matter, galaxies, stars, and potentially very different physical conditions that we may never be able to observe, measure, or influence in any way. The question of how much larger the full universe is than the observable portion is genuinely open. Some estimates, based on the measured flatness of the universe, the fact that its geometry appears to be Euclidean, showing no global curvature, suggest that the full universe could be at least 10 to the power of 23 times larger than the observable portion. Others suggest it could be literally infinite. The honest answer is, we don't know, and we may never know. Beyond the horizon, inflation, the multiverse, and the age of the unknown. We've traveled from the center of the Milky Way out through the local group, through Laniakea, through the cosmic web, to the very edge of what we can see. Now we take the final step, out past the observable universe, into the realm where physics meets philosophy and science meets speculation. To understand what might lie beyond our cosmic horizon, we need to go backward in time to the earliest moments of the universe's existence and look at a theory called inflation. Cosmic inflation, first proposed by theoretical physicist Alan Guth in 1981 and subsequently developed and refined by many others, addresses several puzzling features of the observable universe that the standard Big Bang model alone doesn't adequately explain. Chief among these is the flatness problem. The fact that the geometry of the universe is, as far as we can measure, almost perfectly flat. In the context of general relativity, a flat universe is one that sits at a very specific energy density called the critical density. And small deviations from that density in the early universe would have been amplified enormously over time. For the universe to be as flat as it is today, the conditions at the very beginning must have been set to extraordinary precision. This seems like an improbably fine-tuned coincidence, unless something in the early universe actively flattened it. There is also the horizon problem. The cosmic microwave background is almost perfectly uniform in all directions. The temperature varies by only about 1 part in 100,000. But if you look at two regions of the CMB sky that are on opposite sides of the sky from each other, they were, according to standard Big Bang cosmology, so far apart in the early universe that no light or information could have traveled between them. How did they manage to reach the same temperature? How did they agree to be so similar if they had never been in contact? Inflation resolves this too. Before the inflationary expansion, those regions were indeed in contact, close enough to exchange energy and equilibrate. The expansion then stretched them to opposite sides of the observable universe, preserving their similarity. Inflation proposes that in the first fraction of a second after the Big Bang, somewhere in the neighborhood of 10 to the power of negative 36 seconds, the universe underwent a period of extraordinarily rapid exponential expansion. Space stretched in an almost incomprehensible burst, increasing in scale by a factor of at least 10 to the power of 26, and possibly far more. This expansion would have smoothed out any curvature in the original space, in the same way that inflating a balloon makes its surface appear flat to any observer on it. It would also have taken the small quantum fluctuations present in the original quantum vacuum and stretched them to macroscopic scales. Those fluctuations became the seeds of the cosmic web, the roots of the galaxy clusters and filaments we observe today. Inflation makes predictions that have been tested and confirmed. The pattern of temperature fluctuations in the cosmic microwave background, the faint radio glow that fills the universe in all directions and represents the light emitted roughly 375,000 years after the Big Bang, when the universe had cooled enough for atoms to form, matches the statistical signature that inflation predicts with impressive precision. This is not trivial. Inflation makes quantitative predictions about the shape of the power spectrum of the CMB fluctuations, and those predictions have been verified by measurements from the WMAP and Planck satellites. But inflation has an implication that goes far beyond our observable universe. In most mathematical models of inflation, the mechanism that drives the rapid expansion doesn't stop uniformly everywhere at the same moment. Instead, inflation ends in some regions while continuing in others. The regions where inflation ends form individual bubble universes, each expanding outward and forming their own distinct spacetime. Meanwhile, the inflating background between these bubbles continues to expand, generating more and more bubble universes at an accelerating rate. This is the scenario known as eternal inflation. In it, our observable universe, everything we can see, everything we have ever detected, everything described in this video, is just one bubble among an effectively infinite number of others. Each bubble is its own universe, and the physics inside each bubble may vary. During the inflationary epoch, quantum mechanical effects can set the fundamental constants of nature: the strength of gravity, the mass of the electron, the fine structure constant, differently in each bubble. So while our universe has the specific set of physical laws that allows atoms, stars, planets, and life to exist, other bubble universes may have physical laws under which none of those things are possible. Or they may have laws that are different in ways we cannot predict, allowing forms of complexity that we cannot imagine. It's hard to build models of inflation that don't lead to a multiverse. Alan Guth himself said, "Most inflationary models, when you work out the mathematics, naturally generate the multiverse as a consequence. This doesn't mean the multiverse definitely exists. The bubble universes in the eternal inflation framework are, by construction, causally disconnected from us. No light, no particle, no information of any kind can travel between bubbles. They are, in principle, unobservable, and a hypothesis about something fundamentally unobservable sits on uncomfortable scientific ground. Some physicists have proposed ways to look for signatures of bubble collisions in the cosmic microwave background, places where two adjacent bubble universes might have grazed each other in the early universe, leaving a detectable imprint on the CMB. Searches for such signatures have been conducted and have not found convincing evidence. But absence of evidence is not evidence of absence, and the statistical power of those searches is limited. It is worth sitting with the sheer philosophical weight of the eternal inflation picture for a moment. If it is correct, and many of the world's leading cosmologists take it seriously as a possibility, then the scale of reality dwarfs even the 93 billion light-year observable universe to a degree that makes the observable universe seem vanishingly small. An infinite number of bubble universes, each perhaps comparable in scale to our own observable universe, each with its own physical laws, each with its own history, its own stars and galaxies, and potentially its own forms of complexity and intelligence. Our universe becomes, in this picture, not just one of many, but one of infinitely many. A single note in a symphony of infinite duration being played in an infinite concert hall. Beyond eternal inflation, other frameworks suggest other types of multiplicity. String theory, the leading candidate for a quantum theory of gravity, requires additional spatial dimensions beyond the three we experience. And in the mathematical landscape of string theory solutions, there appear to be an enormous number of distinct vacuum states, each potentially corresponding to a different set of physical constants. Some estimates put the number of distinct string theory vacua at 10 to the power of 500. If each corresponds to a real physical universe, we are embedded in a multiverse so vast that the number of distinct universes exceeds the number of atoms in any individual universe by a margin that makes the word large meaningless. And there are other scenarios, parallel universes arising from the many worlds interpretation of quantum mechanics, where every quantum measurement branches into multiple outcomes, and each branch is an equally real universe. cyclic cosmologies where our universe has contracted and expanded many times before, each cycle potentially resetting initial conditions. Universes with different numbers of spatial dimensions, universes with no time dimension at all, or with multiple time dimensions. These are not all equally well motivated scientifically, and some of them venture firmly into the territory of metaphysics. But the questions they address: what is the universe? How big is it? Are the laws of physics fixed or contingent? Could something beyond our observable horizon operate on different principles? Are the most fundamental questions we can ask, and asking them rigorously and honestly is part of what makes science one of humanity's most extraordinary achievements. The fate of everything, and why this journey matters. All journeys have to end somewhere. Ours ends here, looking back at the breadth of what we've covered and looking forward at where everything is going. The universe has a future, and it is one that cosmologists have spent considerable effort mapping out. In the immediate term, the next few billion years, the story is one of continuing complexity, stars forming and dying, galaxies interacting and merging, the solar system gradually becoming uninhabitable as the sun ages and brightens. The Large Magellanic Cloud will encounter the Milky Way in roughly 2.4 billion years. The Sun will exhaust its hydrogen in about 5 billion years. The fate of our encounter with Andromeda remains genuinely uncertain under the most current models. Stretching further out, to the very long term, the far future of the universe, things become more dramatic. In about 5 to 6 billion years, as dark energy continues to drive cosmic acceleration, the galaxies currently visible in the local group's neighborhood will be the last ones we'll be able to interact with. The galaxies of the Virgo cluster, roughly 50 million light-years away, are already receding faster than we could ever hope to reach them with any spacecraft. Eventually, even the local group's member galaxies will be pulled away. Astronomical objects beyond a certain distance are already, right now, receding from us faster than light, not violating special relativity, which constrains motion through space, but riding the expansion of space itself, which has no such speed limit. In approximately 100 trillion years, the stelliferous era ends. The last red dwarfs, the smallest and most frugal of all stars, will have consumed their hydrogen fuel and faded to darkness. No new stars will form, because the gas supply available for star formation will have been exhausted. The galaxy, the merged remnant of whatever the Milky Way, Andromeda, and the other local group members become, will be a dark, cold graveyard of burned-out stellar remnants, white dwarfs cooling toward absolute zero, neutron stars spinning down, black holes growing slowly larger by absorbing any matter that wanders close. The black holes will be the last lights in the universe. Over timescales so vast they require scientific notation to write roughly 10 to the power of 64 years for stellar mass black holes, 10 to the power of 100 years for supermassive ones. Even black holes are not eternal. Stephen Hawking showed theoretically that black holes emit a quantum form of thermal radiation, now called Hawking radiation, and slowly lose mass over time, on long enough timescales. Every black hole in the universe eventually evaporates completely, releasing its mass back into a thin gas of photons and subatomic particles. What remains after that? What the universe looks like in the far future, if current cosmological models are correct, is a cold, dark, almost empty expanse of space. The temperature of this universe will approach, but never quite reach, absolute zero. The density will be almost nothing. The expansion will continue forever if dark energy remains constant, stretching the remaining photons and particles into an ever more dilute and featureless background. This final state is sometimes called the heat death of the universe, and it is as close to true nothingness as physics allows while still having something. But here's where things get genuinely uncertain. In 2026, research from Cornell University analyzing new dark energy data raised the possibility, controversial but not dismissible, that dark energy may not be constant. If dark energy is a dynamic quantity, one that can change over time, the future becomes fundamentally unpredictable. Some models with evolving dark energy predict that the universe could eventually stop expanding and begin to contract, ending in a big crunch, a collapse back into an unimaginably hot, dense state. One recent analysis suggested this might occur roughly 20 billion years from now, if certain dark energy models are correct. The universe, in that scenario, is not even at the halfway point of its lifespan. The truth is, we don't know. The nature of dark energy remains one of the most pressing open questions in all of physics, and the answer will determine the fate of everything. And yes, sitting with all of this, from Sagittarius A to the Hercules Corona Borealis Great Wall, from the Magellanic Clouds to the edge of the observable universe, from inflation's violent birth of space-time to the potential slow death of everything, what strikes me is not the scale. Scale can feel numbing if you're not careful. What strikes me is the fact that we figured any of this out at all. We are a species that has been fully anatomically modern for only about 300,000 years. We invented writing about 5,000 years ago. We discovered that the Earth orbits the Sun less than 500 years ago. We worked out the existence of other galaxies only about 100 years ago. We imaged a black hole for the first time in 2019. We photographed our own galactic black hole in 2022. In the span of a single human lifetime, the observable universe grew from our galaxy alone to a structure containing 2 trillion galaxies. That rate of discovery, that rate of expanding the known, is one of the most extraordinary things about the era we happen to be living in. There is more to learn than we can possibly learn. Every answer in this video contains 10 questions. Every structure we've named tonight has details we haven't worked out, behaviors that surprise us, implications we haven't fully traced. The universe is not a solved problem. It is the unsolved problem, the grandest and most persistent question humanity has ever asked, and every generation gets to contribute its piece. Whatever lies beyond the edge of the observable universe, whether it is more of the same, or something genuinely different, or the curled boundary of a finite space, or one of infinitely many bubble universes floating in an inflationary background, it will never stop being interesting. The universe does not run out of things to show us, and that ultimately is why we look up. If this journey gave you something to think about, a new way of seeing the sky, a new appreciation for the scale of what we're all a part of, then something went right here. These are the questions that keep astronomers up at night and fill the pages of the journals where science actually happens. And every time we zoom out another level, we find that the universe has been holding something back, waiting to surprise us again. If you want to keep going deeper into the science, into the mysteries, into the parts of the cosmos we haven't explored yet, make sure you hit that subscribe button and the notification bell so you don't miss what's coming next. We have a lot more universe to cover, and we're just getting started. Leave a comment below and tell me which part of today's journey hit you hardest for you. I read them all. And as always, keep looking up,